Hi guys, back in my lab. As yet, nobody else is, but hopefully that might change. But I'd like to do some videos on rates of reaction, which might help you a little bit. They're not going to be able to cover like hours and hours of teaching. I won't be able to do that, but at least I can give you some idea about what rates is at A2, how it relates to AS, and all that sort of thing. Okay, so we'll give it a go. So, rates of reaction. Hope you can see that all right. There you go. Rates of reaction. Okay, so rates of reaction is based on particles colliding. Okay, so we'll start on something as simple as I possibly can. Okay, let's have a look at, say, hydrochloric acid. Okay, aqueous. It's a solution. That's important in rates, the fact that it's a solution. Let's say, so it's particles in a solution of a certain concentration. Let's say it's reacting in a simple reaction with sodium hydroxide. Okay, again, that's aqueous solution. So it's got a concentration, which we can alter the concentration of this, and we can alter the concentration of that. Okay, and the particles will bash into each other, and they will make sodium chloride and water. Aqueous. Okay. I might be able to get a pen that's actually any good in a minute. It doesn't run out 2 seconds flat. Okay, now you could say, right, in order for this reaction to happen, particles of this must collide with particles of that. So maybe it's straightforward. Maybe a particle of hydrochloric acid bashes into a particle of sodium hydroxide, like that, bang, bang, bang. Some magic occurs, and they make the product. They make sodium chloride and water. So these two particles bash in, whizzing around in aqueous solution, bang, they bash in, and they make the products of the reaction up here. Okay, maybe that's what happens. But reactions are not as simple as that. Reactions occur through complicated mechanisms. Okay, there might be intermediates involved. Maybe it's not straightforward. And really, the end of this topic, we use rates and the influence of various reactants to try and deduce the reaction mechanism. Is there any intermediates in the reaction mechanism? Does it proceed by a specific route? Okay, and the data that we get from rates experiments allows us to deduce how a reaction mechanism proceeds. Okay, because they aren't necessarily as straightforward as that particle bashing into that particle to make that and that. Maybe there is more to it, but we don't know. So the whole thrust of rates is to use evidence to try and deduce what's happened, and that comes right at the end, but it's worth mentioning it at the start. Okay, maybe to give you some example, right, to show you where I'm coming from, hydrochloric acid particle bashes into a sodium hydroxide particle, like that, bash in, okay, and forms some kind of intermediate that's, you can't isolate, it may be charged, it may not be charged, like an intermediate in organic chemistry when you form a charged particle, a carbocation in a mechanism. You know, you can't isolate these things, but the reaction proceeds through one of these species, okay? Yeah, so maybe that bashes into that, and, that hydrochloric acid bashes into another particle of hydrochloric acid first, right, and forms some strange transitory intermediate, like that, right? Which isn't a product, but it's a route by which the reaction proceeds. Okay? And maybe this transitory intermediate then splashes into sodium hydroxide and maybe then goes on to make the products. What I'm trying to say is, so different reactions proceed by different routes, like that. It's not necessarily as straightforward as one particle of that flashing into one particle of that. Okay? So, perhaps the next thing to say, just so be flexible about how reactions actually proceed, rather than, which may be very different from the overall balanced equation, which tells you nothing about how that reaction will proceed. Okay, different routes, right? Bear that in mind. Okay, so take that. Right. So next thing is experimental data. Okay, right. If you're going to look at how changing the amounts of different reactions changes the rate of the reaction, you need to be able to calculate the rate. You need to have some idea of how that reaction is actually proceeding, and you need something visual, and this relates straight to A2, straight to AS. In other words, any rates experiment must produce, say, a gas or a mass loss that you can continually use, some physical quantity that you can continually use to monitor the rate of the reaction. Okay, so for example, we've seen these at AS, so you might have a reaction such as this, taken from an AS paper, right? Some reaction between sulfur dioxide and oxygen to make sulfur trioxide. Okay, that's a reaction, no problem. How can you monitor how fast that reaction is going? Sulfur trioxide is a gas, so a gas will be produced. So you can measure that gas and you can use the way that gas is being produced. So could be volume against time. And you can tinker around with the concentration of this or the concentration of that, and you can see how the rate of sulfur dioxide concentration changes as the reaction proceeds. Now this doesn't give you the rate. This is pure AS. You need to draw a tangent, and you need to draw a tangent at t equals 0, because t equals 0 is called the initial rate. Right? And we tend, when we're comparing rates, to use the initial rate. Okay, sure, you can take a tangent wherever you like. You can take a tangent after, I don't know, 20 seconds or something, and you can do a tangent there, and the rate will have slowed down. Okay, and you can measure the gradient and calculate the rate at 20 seconds or at 10 seconds. But that leads to problems in comparison of rates data. You have to have a sort of a standard. So it tends to be the initial rate, because that's the fastest rate of the reaction. Both all the particles are in their maximum concentration. The experiment's going to go fast, so you can compare one rate with another. So that's how we know how a reaction goes. And there are various techniques for doing that. So to give you another example over here, let's think about this. I don't know, strontium carbonate plus nitric acid makes strontium nitrate. These are just random, okay? Plus water plus CO2, the all-important CO2. So this, you can measure the rate, that you can measure the how the CO2 is being produced over time, and then you can calculate the initial rate. So in other words, one way to measure or to deduce the rate of an experiment is evolution of a gas. If a gas is evolved, you've got a handle on that experiment. So evolution of gas. Okay? That type of thing. That gives you a handle. Tinker with the concentration of that, tinker with the concentration of that. Does it affect the rate? What rate? Why does it affect the rate? What can you deduce? Okay, but you've got an it. Another one might be evolution of a gas, and then maybe you put your conical flask on a balance. Okay, and as the gas is evolved, we've seen this many times. Okay, mass loss, you would call that. So you can still measure the rate, except you're going to get a graph that looks like that. And you can measure the rate there, the initial rate, because of course the reactants are going to get lighter as the gas is evolved. So mass loss, number 2. But there are others, for example, coloured. This is one that's quite popular. Coloured reactants. Coloured products. Okay, well, if you have a colorimeter which will measure the intensity of that colour, okay, you can use the way that colour, maybe if the reactant is coloured, it will, let's say it's brown, right, it will get lighter and lighter as that reactant is used up. So you will get a graph maybe of colour against time, and you can do a rate. How that colour is, because you can relate the colour to the concentration, they're directly applicable, directly related. Concentration of a particular coloured reactant goes down. Colour of a particular reactant goes down. You can get a graph produced experimentally. If you've got this colorimeter, you can draw a line, do a tangent, calculate the gradient, and you've got an into how fast that experiment is proceeding. Again, you could have the colour of a product. So the colour of a product is going to get, let's say the product is, I don't know, red, right? Then it's going to go pink and darker red as the reaction proceeds. If you've got a colorimeter, you'll get perhaps a graph like that as the red colour goes darker. If it's the product, it's going to get darker. It's going to get lighter if it's the reactant as it's used up. It's going to get darker if it's the product as it's created from the reaction. There are other ways to measure the rate. We'll come back to all this, like I say. This is more of an introduction, some ideas of what you need. pH, okay? You can continuously measure the pH, how it changes. So let's say we might have a reaction like, I don't know, concentration, I'll go straight back up to here. Nitric acid. Okay, now the concentration of that nitric acid is going to go down as the reaction proceeds at a certain speed, which you can calculate the rate as it goes as the concentration decreases. But you can't look and see concentration, but if you put a pH meter in, then the concentration of this acid as it's used up in the reaction will decrease. You're going to get a graph that, rather than colour, pH decreases as the nitric acid is used up. So there is a number of different ways to measure the progress of a reaction and calculate the rate of the reaction. So it doesn't matter how you do it, but you've got to have some way of measuring how that reaction is proceeding. Okay, so 2 things I want you to take from that. Different mechanism. You've got an equation. That is not how a reaction proceeds. We'll do a rate equation later, which is totally different from the overall molar ratio equation. Okay, totally different. That tells you the reacting quantities. The rate equation tells you how each particular reactant influences the rate. Totally separate. Okay, so that's a bit of a quick, I would say, overview. I'll pause this for a minute if I can.